about optimality and approximation with policy gradient methods.
Thanks, Ohad, and thanks to the organizers for having me. Try to keep things pretty interactive, so if anything is not clear, feel free to ask a question. Let me start by thanking my amazing collaborators on this work. So this was done jointly with Shyam at UW, Jason, who's here and moving to Princeton soon, and Gaurav, who's a student at UCSD, who also did spend a bunch of time this summer here. And thanks to Simons for at least like keeping Jason and Gaurav in the same place, because as you can see, we all come from different institutions otherwise. This talk is going to look at a particular class of methods in reinforcement learning. And just for contrast, because the morning was mostly all about value function methods, we're going to talk about these policy-based methods in this talk. And these methods are actually quite widely used in practice because they're kind of, in a way, the most direct approach to solving the reinforcement learning problem. You want to find a good policy, and you do it by actually optimizing the value of the policy by running some gradient-based optimization algorithms. These methods are quite nice and flexible in that they can be extended to handle continuous as well as discrete states and actions. And they basically work as long as you have a differentiable policy parameterization. So they're quite convenient in practice. In contrast, though, the theoretical understanding is somewhat coarse-grained for these methods. So, okay, we are doing basically a stochastic gradient type method. So we know that with sufficient smoothness of the objective, we will find a stationary point. We can quantify the rates of convergence for that, and so on and so forth. But that's not quite satisfying, right? We would really like to understand when and how well do these methods work. How long does it take them to maybe find a globally optimal solution, and so on and so forth. Right. So that's the style of questions we want to answer. Suppose we were in the simplest reinforcement learning setting where we can represent any possible policy in our parameterization. Would these methods find a globally optimal policy? When we don't have such a luxury of representing every possible policy, what happens? How does the approximation error start to factor in? And what happens when you're doing all of this with a finite amount of data? How does that interplay with our convergence rates? Right. So these are the types of questions on which I will try to shed some light in this talk. But before I do that, let me also highlight why this is a challenging problem. So first of all, for most natural MDPs and function parameterizations, the underlying maximization problem is typically non-concave. Now, it's a brave new world. Non-concavity doesn't scare people anymore. So that's by itself not enough of a deterrent. However, what we'll see is also this interplays in a somewhat critical manner with the exploration problem that is somewhat unique to reinforcement learning. And in particular, when you don't do good exploration, your gradient algorithms might get stuck in poor local optima, poor stationary points. So that's something we have to be cautious for. Again, like how all of that interplays with function approximation can be somewhat challenging to quantify. So I'll start by introducing some preliminaries. The previous speakers in the session have done an excellent job of introducing most of the concepts. So we can be a bit quicker about this. And then I will first start by thinking about the most basic tabular setting, where we can represent any possible policy, and then move to the more interesting approximate case. OK. So starting with the preliminaries, we will be in the discounted Markov decision process setting. So we have a state space, an action space. We'll typically think of the action space as small and finite. For the state space, in the initial part, when I'm talking about the tabular setting, it's good to think of it as small. But then when we move to the approximation setting, state space can be large as we like. There's a reward function R, transition operator P, and a discount factor gamma, but in 0, 1. We want to find policies which are mappings from states to distribution over actions. So they are in agents, basically decision rule. For every policy, there's this object that will keep coming up, which is the state distribution that the policy induces. So what this says is that if you start from an initial state as 0, and then take all actions according to pi, and state transitions happen according to MDP dynamics, then you can look at the discounted sum of the amount, the probability with which you visit a particular state S at different time steps. The 1 minus gamma upfront just serves to normalize the thing so that the whole object is still a valid probability distribution. And this is kind of convenient because it helps us write down things like the value functions induced by a policy in a fairly concise manner, right? So the state value function of a policy is just the expected reward under the state visitation distribution, and the Q functions are basically on this particular state you took some action here, but then you follow the policy and then you account for the long-term reward, right? So these are pretty standard objects. Now, the other thing we need to think about when we are especially running policy optimization algorithms is how we are going to represent our policies. So usually we want to, have some space of parameters theta, and each choice small theta in the set big theta induces a particular policy. We can represent the whole policy class by capital pi, and we want to find the best policy in this class, where best is measured in terms of the amount of value the policy achieves starting from some initial distribution over states. That's represented by rho here. Okay, so we have some initial distribution over states that we care about. This can be, for instance, in the examples before, like the initial configuration of a game screen, initial configuration of a robotic agent, so on and so forth. And we want to find a policy that induces good long-term value starting in that state distribution. And we want to find the best policy from this class. A very simple parameterization that I will focus on for a bulk of this talk is the so-called softmax parameterization, where so this is for now in the tabular setting. So we have one parameter for every state and action. The probability of taking an action in a state is proportional to the exponential of this parameter. We normalize. And because we have one parameter for every state and action, and the functional form here is such that we can really represent any possible policy. I mean, okay, if you want to represent a deterministic policy, you might have to send some things off to infinity, and that's going to cause maybe some problems later on. But this is a pretty commonly used parameterization that we'll stick to for the initial part of the talk. And when we in the later part, when we start talking about approximation, then pi will really be a restricted class and need not contain the best unconstrained policy. Okay, so what is this policy gradient algorithm? As you might imagine from the name, it is really running gradient ascent on the value of the policy, which is the objective we want to maximize. The only maybe twist to pay a little bit of attention to, you can ignore it for now. Its role will become clearer in the sequel. So sometimes the initial distribution over states from which we will start our algorithm might be different from the distribution rho that we care about, just as an exploratory device. So maybe when we are trying to find a good policy, we might actually put the robotic arm in all sorts of weird configurations initially, and that's going to be useful to explore the state space well. And its role will become clearer as we go through the talk. But suppose we commit to some initial distribution over states for the algorithm, denoted by mu here. Then the algorithm is literally running gradient ascent in the parameter space. And Vt here represents the value function using the parameters, the policy induced by theta t. Right, so okay, I didn't want to use V of pi of theta t, so I'll always abbreviate that using Vt. And the reason, okay, so far, I mean, this might, while conceptually look nice, it might be, we don't know. I don't really have the MDP in my head, so I might not be analytically able to compute this derivative, and that might seem like a blocker. But the reason these algorithms have been popular is that really this derivative is something we can estimate from data, right? So this is basically a consequence of these very nice policy gradient theorems which show that this, you can write this gradient down as an expectation over states and actions that are, so the actions are all chosen according to pi, and states come from the corresponding state distribution that is induced by pi. And you take the expectation of this function, which is the derivative of the log policy, times the q value function of the policy. And this q value function is the thing we looked at before, which is saying if you take action A in state S and then follow the policy thereafter, what is the discounted long-term reward you get. And without really worrying about the details, the important bit is that you can obtain unbiased estimates of this quantity from data, so we can really bring our stochastic gradient methods to bear on this problem. Okay, any questions so far about the basics? Okay, and because I'm focusing on the softmax parameterization for the initial part of the talk, it really gives rise to a very interpretable policy gradient that I want to show you, because it will, in one formula, it summarizes both the good and bad aspects of this algorithm. So if I take the value function of a policy and differentiate it with respect to a particular parameter for the state SA, it takes the following form. So don't worry about the scaling up front. Okay, so there are three things coming in this equation, and let's worry about them one by one. So first I have this symbol A. So this is what's called the advantage function of a policy. What it measures is, you are in state S. You could have done two things. You could have just chosen the action A, or you could have listened to the action distribution that pi induces. Once you, with respect to either of the, after you've made that choice, you commit to following pi for the remainder of the MDP still. Right, so you're just worrying about, for this particular state S that you're in, whether you're going to act according to A or act according to the policy pi. And the difference between these two basically lets you measure the effect of a local change you can make by preferring action A over the current policy's action distribution. Right, and it makes sense that if an action A induces a significantly larger reward than what the policy gets, then updating our parameters to actually start favoring this action is a good thing, right? It's a good local improvement to make. And that's kind of what this gradient expression is doing. It's saying that if you see an advantage on an action, meaning that this action, leaving the policy fixed everywhere else, just starting to favor this action is a good thing, go for it. Improve your probability on that action. So that's great. But then this advantage gets scaled by the state and action probabilities for that particular SA pair. Which means if you're a policy that you don't really feel like improving upon yourself, you can sort of bury your head in the sand. You can say, well, I'll just ignore all the actions that have advantages over me by putting 0 probabilities on them. And look, I'm stationary. Nobody can improve upon me from the lens of the gradient. Right, and that's kind of the problem with this algorithm, that it can have these bad stationary points if better actions are not explored by the policy itself. And that's going to be one of the key difficulties in trying to analyze these algorithms. Nonetheless, we do want to understand these algorithms. So let's start with the most basic case. Let's say we have this softmax parameterization with one parameter per state action pair. We start from an initial state distribution that is non-negative in every state, or sorry, strictly positive in every state. Then with an appropriate step size, you will actually asymptotically converge to the globally optimal policy in the MDP. That's pretty cool. It's saying that you are in this non-concave optimization maximization problem, but the gradient-based updates will find your globally optimal policy. Now we can think about why that happens a little bit. Again, going back to this expression. Sorry. What happens? Softmax, because of the functional form, puts non-zero probabilities on every action in every state, right? Unless, I mean, some parameter truly is infinite, you have some non-zero probability of trying everything. And that sort of makes sure that you cannot fully bury your head in the sand. Now you have to be careful, because now we are talking about things that can actually be non-zero but can be converging to zero in the limit. So the proof ends up being quite technical for this. And really the other reason the proof ends up being quite technical is because in the limit you're trying to converge to an optimal policy which is deterministic. So you really are sending a lot of thetas off to infinities in the limit, and that creates a lot of mathematical headaches. But the conclusion is kind of nice.
I'm just a little confused. Where is the data being used in the gradient update?
Great question. So yes, thanks for bringing this up. I forgot to point this out. For most of the talk, I'm going to actually worry about exact policy gradient methods, which means I'm assuming you have the exact gradient. There are no samples involved. I'll talk in one slide about what happens once we start introducing finite samples, and the paper does go into the details there. But it's actually kind of nice to just think about algorithms that have good or bad behavior even with exact gradients, because some of the things we'll see are, it's not going to be all like hunky-dory. There will be troubles that come up. Isha.
Do you have like a rate also?
No, this is totally asymptotic. I have absolutely no idea what the rate is. It's probably very slow. I will talk about convergence rates by trying to fix some of the deficiencies of this algorithm in a minute. Nan.
Yeah, you know that if you run this in combination log, you will get exponential, right?
But this is with exact gradient.
Even with exact gradient. Because in combination log, if you start with like
yes.
uniform,
yes.
gradient is exponentially small.
Right.
So this proof is one of these stable manifold theorem type proofs, where you prove the policy gradient map is smooth and.
No, okay, yes. So we do use smoothness to show that we are making monotonic progress and so on, but there is still a lot of other things that need to be done because thetas are growing to infinities. That will.
But it's still a variant of one of these stable manifold theorem type things where you kind of go backwards from.
No.
Oh, okay.
Okay, but really, the point is that this result, while it's saying that the algorithm is doing something sane, shouldn't get us too excited, because it truly is an asymptotic result, and I don't think the convergence rate is going to be very nice here, and Nan makes a valid point that in some cases it will be exponential. And partly it is because we are really relying on these non-zero probabilities, which are going to be very small though. So if small probabilities are worrying us, then there's a very standard solution in the literature to think about fixing that, both in terms of the solution we are trying to converge to and the path that our algorithm follows, by actually adding some regularization to keep the probabilities policy induces bounded away from zero. Right. So this one, and a lot of these are entropy-based regularizations. So that's what I'm showing here. So we take the value function of a policy and we add some penalty. So here I'm measuring the penalty is KL between a uniform distribution over actions and your policy's probability, which can be further simplified. So it's just like a log barrier, keeping your probabilities from going to zero. Okay, so one thing to.
What do you mean by probability are small?
So pi theta of a given s, the action probabilities in any state.
Why is that the reason? It converges very slowly?
Because our gradients are proportional to pi theta of a given s, at least in the softmax parameterization, right? So your gradient, even if you have a large advantage on some action, the gradient might be very small spuriously because the policy puts a small mass there. Now one thing to note is, by the way, this is like usually people would often do the KL in the opposite direction where pi theta is the first argument. We found that this one is actually, at least for theory, more convenient and better because this function actually grows much faster when you're closer to zero than entropy, right? Entropy is always a bounded function. This will actually blow up. So that actually ends up being nicer in terms of convergence properties. And we want to now study the following modified policy gradient algorithm where we take gradient steps on this regularized objective. Matos?
Do you know anything about, in practice, if switching the scale makes the difference?
I will No. I mean, people there are some kind of informal things, but not really anything that has been very rigorously studied, at least to my knowledge. Okay, so adding this regularization does indeed have some nice effect in that we can really extract a convergence rate now to address Yishai's comment. So what I'm saying is that if you run t iterations of this regularized algorithm, the best of the iterates you will find will be approximately optimal. Now the approximation is given by, okay, so we have some polynomial dependence here. So we have linear on state and action. We have a cubic in this effective horizon. We have square root of t with respect to number of iterations. But I'm introducing a new quantity here. So let's focus on that for a moment. So what this quantity m measures is, so for any policy pi, m would measure the state distribution that pi induces and the initial state distribution that you begin with in policy optimization. How much bad can the ratio be in any particular state? And we in particular care about this for pi equals pi star. Okay, so I mean the max over all states here is not very nice. However, when that max is truly infinite, I can actually give you counterexamples where this algorithm will not work. So it's at least not a completely superfluous dependence. The other thing is, by the way, so Nan was talking about similar density ratio type assumptions in the morning. The interesting difference here is that this quantity, for every MDP, there is a distribution mu, which makes this quantity finite, which is just the state distribution induced by pi star. So while this is an assumption about what the algorithm gets as input, it's placing no restriction on the MDP dynamics, unlike these concentrability type of quantities that some of the value function based algorithms seem to need. Mohammed?
So this B star is the optimal policy of the soft MDP or the original MDP?
Of the original MDP, I believe. Yes, that's a good point.
Why does the mismatch ratio depend only on pi star but not on the sequence of pi's leading to pi star? So what's preventing it?
That's all the proof needs. I mean, it would be bad if it actually needed to depend on. In fact, really, it only depends on. You could even replace mu here with kind of like the policies you find along the sample path. It's really the ratio between the state distributions that pi star induces and the policies that you are producing induce. And mu is just like a universal lower bound on that up to a factor of 1 minus gamma.
And I think maybe one intuition is that when you invoke the value difference lemma,
yeah,
you get something like you can write the suboptimality of your current policy as under the distribution induced by pi star. What's your kind of like advantage with respect to your current policy?
Yes, so exactly, like the technical reason is exactly shows up through the performance difference lemma where you care about your advantages under pi star, gradient gives you advantages under pi, so it's the ratio of the two distribution that affects, that can cause problems.
If I understand correctly, so if I assume mu is some uniform distribution, as for example, then this m is like s.
Exactly. Yes. So that's
you actually need t to be like s to the fourth a squared to converge something.
Yes. Keep in mind that we knew nothing about this algorithm before.
Okay.
So in the worst case, it seems that m could be bigger than s. It may depend on the mixing time, etc.
Yes. So okay. So two things kind of important is that, like the way I've described, mu need not be a distribution that you're even inducing through a policy. Like if you can really if you have a simulatable environment that you can restart in different types of states, then mu might be something that does not need to depend on mixing time type properties. But if you're right that if I restrict mu to distributions that I can induce in the MDP by acting according to policies, then there will be additional nuances other than the number of states that will start popping up.
And just a minor question, you've normalized the value here, right? So this.
I have not. I have not normalized the values.
So then,
the values are in 0h.
Okay, so then the cubic dependence on horizon, like two of them are superficial.
3. No, it's like if I translate to epsilon squared, it's going to be gamma 6. 1 minus gamma to the 6.
Okay.
Do the parameters depend on m? Does the algorithm have to know it?
No. I have a detailed theorem I can show you later, which it just. The other thing, by the way, I want to highlight here is right. I always used to think that exploration is a phenomenon that is about data efficiency, right? So it should matter when we are thinking about finite samples. But what kind of is important to observe here is that we are actually in an exact gradient setting. There is no data that has come in yet, but the exploratory property of the algorithm still matters. And okay, like in hindsight, it should be pretty darn obvious if the policy doesn't go somewhere, like you can collect as much data as you like with it, but it's still at least a little bit non-intuitive when I first saw it.
Maybe it's also worth pointing out that this exact M quantity has also shown up in the analysis of the CPI.
CPI algorithm. Thanks, I forgot to point that out. So yes, this is not a quantity that we are introducing here for the first time. The first reference I know of is Kakaday and Langford in the analysis of CPI. The same quantity shows up in trying to show the global optimality. Other questions? Okay, good. So okay, so this is our this is what we've seen so far. Now we would like to do better, and really the thing that seems to be blocking us, or the thing that seems to be the reason for this distribution mismatch, is because our gradients are scaled by the state distribution of pi. So if you could somehow get a gradient that was not scaled by this quantity, that would be fantastic, because we would get a large signal whenever there is a large advantage. It turns out an algorithm that does that has been around for almost 2 decades now, and this is this natural policy gradient algorithm. I'm not going to give you the general form of the algorithm yet, we'll see that later, but I'll just simplify it for the particular softmax parameterization, because it just simplifies so nicely, it's hard to resist. So this is still a first order algorithm, but it is a preconditioned first order algorithm that uses a Fisher information for preconditioning. And when you write it down for the softmax parameterization, really a lot of nice cancellations happen, and you get this very, very nice update where the parameters are basically being updated as if you were doing online linear optimization with your linear functions based on the advantage of the current policy. And by the softmax form, your policies are basically doing these multiplicative weight updates with the exponential of the advantages. So that's great. First of all, these do not depend anywhere on the state distribution. The Fisher information took care of that. Secondly, these are multiplicative weights, which we have, again, decades of literature trying to give us tools for understanding that algorithm. And indeed, we bring those tools to bear, and you start getting some really nice guarantees now, where you can say that, well, you will find a policy at a rate whose suboptimality vanishes at a rate that is completely independent of states and actions, quadratic in horizon, and 1/t. Okay, so this is truly a dimension-free convergence guarantee. Does not depend also on the distribution mismatch coefficient. I want to point out that people who are studying approximate policy iteration, they had been looking at entropy regularized policy iteration type algorithms and had derived very similar looking updates without necessarily connecting those to natural policy gradient, but had similar but slightly worse results for the same type of update rule. And since actually the analysis is actually quite simple, so I want to just give some brief intuition about it. So this is the basic lemma that is from the CPI paper that Nan was referring to. It really is a tool to understand the difference between two policies in terms of the state action distribution of one policy and the advantage function of the other policy. And for our purposes, we can parse this lemma in a very functional form. When we try to analyze multiplicative weight type algorithms, the first thing, like especially or exponentiated gradient algorithms, the first thing you do is you go from, you use convexity of your objective to linearize the regret with the first order Taylor approximation, and then you study the online linear optimization problem induced by gradients. Well, here you basically do the same thing, except this lemma, where you treat this as your optimization variable, this part comes from pi star, and this part comes from your current iterate. So you just linearize things using a different lemma instead of Taylor's theorem. And then we are off to the races. We are in our standard online linear optimization setting, and 1 over root t rate follows almost immediately. You have to work a little bit harder to get 1 over t by lower bounding the amount of improvement you do per step, but that can be done. Okay, so really quite a simple analysis if you are familiar with the online learning literature. Right, so that kind of brings us here.
Is that just mirror descent or some sort of mirror descent?
It's multiplicative weight. So yeah, it's mirror descent with relative entropy, right? So since we are kind of improving our algorithms, at least in my opinion, as we are going down the table, now if we would like to study function approximation, it seems we should take our best candidate from this table and try to study what happens to it when we go to approximate settings, and that's going to be the second part of this talk. So any questions before yeah?
One depends on epsilon, one depends on t. Right?
Yeah, that should be.
Oh, sorry, t should be epsilon here. This is a 1 over epsilon rate. Sorry, yeah, I switched my rates from the t based to epsilon based last moment. Good. So now we'll talk about restricted parameterizations, and nothing much is changing. This is mostly just a recap. So remind you, we have a constrained policy class. So now we truly want to compete with the best policy in the class, though. We no longer necessarily assume that we can find the best unrestricted policy, and maybe a good canonical example to carry in our minds. I'm not going to rely on this particular parameterization the way I was relying on Softmax before, but it's still a good kind of extension of it to keep in mind as a motivating example, where now we think that we have some state action features, for instance, like the example Smingdi was giving in the morning. But unlike the previous case where we had one parameter for every state action pair, now we only have d parameters for some d which is much smaller than the size of state and action spaces, and S can even be infinite at this point for all I care. Right, and we want to find the parameter theta now that induces the best policy in this parameterization or under a different parameterization. So in order to think about the algorithm we want to use here, now we really want to look at the general form of natural policy gradient, and do apologize, there are quite a few symbols here, so we'll try to parse them together. So really, okay, let's start from here. All that natural policy gradient is doing, it's doing a preconditioned first order update, right? So you have the same gradient as before, but now you hit it with the pseudo inverse of this Fisher information matrix. And the Fisher information matrix is just an expectation of gradient outer product where the gradient is of the log policy. Okay? If that looks too much, don't worry, the specifics don't matter really. But one thing that may be is at least if you remember that this gradient also involves the gradient of log policy times the advantage or Q function, then one thing that maybe might start looking familiar somewhere in the back of the head is that this is looking very much like an ordinary least square solution, right? You have something that kind of looks like x transpose x inverse x transpose y, where x is really this gradient. And that is actually indeed the case. You can formally write down this loss function which is trying to approximate the advantage with some weights times these gradients. And this would be the OLS solution for this least squares minimization problem. And this loss function is not new to the policy gradient community, by the way. It was really part of the certain 99 paper where they sort of also realized that this is a pretty nice loss function in terms of thinking about the expressivity of a policy class for these types of policy gradient methods. But and the other, if all of that looks very technical, here is a good example to think through when we are thinking about the linear softmax policies. Then the gradient basically you can replace by the state action features. So you're really asking how well do my features using linear functions help me explain the advantage function of the policy. That's a measure of the expressivity of my features that we'll be using. Okay, but realizing that what natural gradient is using is a solution to this least squares problem lets us write kind of a pretty intuitive general algorithm where, okay, we'll find any minimizer of the least squares under the current state distribution, under the current policy. Then we'll perform a parameter update by moving in the direction of the minimizer, which is kind of what this thing is doing, right? So very similar algorithm does exist in the literature. It's called natural actor critic, introduced in the work of Peters and Schall. But we were not aware of any prior analysis of this algorithm, which is the goal here. To do that, I do need to make a few assumptions. So let's. I don't think any of them is kind of too bad enough itself. So the first one is just saying that these gradients of the log policy are Lipschitz continuous. So the policy has some. The log policy is basically a smooth function. Linear softmax would satisfy this easily if the features are bounded. The second one is saying that the weights that I induce to solve these regression problems, they need to have a bounded norm as well. The third one starts to quantify the approximation properties of our policy class, of our parameterization really. So it says that when I find the best regression weights here, I want to have a small regression error. For instance, if you did the tabular softmax version, then this epsilon approx would just be 0 if you did the minimization exactly. So this is really a measure of expressivity. And the fourth one that actually is not strictly necessary, as we'll see, we can replace it by something more general, but is convenient, is to assert that the initial, so now we'll have both the initial state and action distribution, and the initial action distribution has a bounded minimum probability over each action. Okay, so the bottom line is that if you have these assumptions, then you will find the best parameter in your parameter set, where the best parameter is in terms of, again, the value function with a suitable step size. Okay, so let's parse the result slowly. First thing is that we do only manage to get a 1 over root t rate here instead of the 1 over t from the tabular case. I actually do know how to get 1 over t, but it requires making some assumptions that I do think are outrageous. So that's why I prefer the slower rate instead. Unfortunately, our old friend distribution mismatch coefficient is back here. And basically the reason it comes up is when you're, really the notion of approximation you would like to control is under the state distribution of pi star. But in the algorithm we can only expect to control it for pi. But that's kind of a useful intuition to keep, because you're now talking about how well does the solution to one regression problem generalize, regression problem under one distribution generalized to doing regression under another distribution. So this is more like regular sort of transfer learning and regression. And while I'm being very pessimistic here in terms of measuring similarity using L infinity norms, we do have more refined measures of when and how well can we do effective transfer that can potentially be brought to bear here, right? So the regression-based intuition is actually kind of useful to keep in mind. And finally, the effect of function approximation is captured in terms of this quantity. Nan?
Actually, so for this M thing that depends on pi star,
Yeah.
can you actually just replace it by something like, I can compete with any theta, and my regret with respect to any theta
Yeah.
scales with the M of that theta?
Yes, that's the result the paper proves.
And I can take the best guarantee over,
Yes.
over all thetas.
Correct.
Yeah, okay.
Yeah, so technically, yeah, your regret with respect to like a particular theta here will be for that the M that theta induces. That's a good point. Okay. Anything else?
So in the analysis, do you use the epsilon approx to make it kind of seem like a convex problem or a concave problem, and then you can still use some merit descending thing like you did before, or?
Yeah, so we do kind of use the fact that this is like a regression problem. I mean, but the way to think about it is that this is like the thing that's going to appear when you apply performance difference lemma. This is the thing that if it appeared, you know how to actually do the analysis by the same analysis we did before in the tabular case, and the gap between the two is epsilon approx. So the actual like thing that first comes out is this. You try to replace it by that and pay the epsilon approx.
And this epsilon approx is still that kind of like, you basically need the same set of features to realize like all these regression targets for all like at least all policies that you encounter along the way.
Yes, I mean, okay, if you have some fancy way of like, here is a policy, write down these features for that policy, then sure, maybe you could do something. But here, yes, there is the same set of features being used to express every policy's advantage function. So yes, we do require all of them to be expressible in the same basis. The other thing I want to, by the way, highlight is, so with regards to this regression problem, like I said, we can solve this under theta. We care about solving it, for instance, under theta star, and that's where I'm paying the ratio of the two distributions. So now in the distribution mismatch, I'm kind of doing like an L infinity L1 holder, right, where I'm pulling the worst case distribution ratio out. But if you didn't want to pay worst case, like you can obviously knock yourself out with all possible other holders that you could do here if you have any information that, for instance, allows you to control the density ratio in some other norm. So that's kind of another easy lever we have to pull here. Mohammed.
And so you don't care about the function approximation for D because you assume that the gradient is calculable, right? Because I don't see anywhere that approximation appears.
Function approximation for V will not matter even with finitely many samples. So I might as well talk about it. Okay. So look, the point is, the advantage function, which is really all I care about here, I can estimate it from even one trajectory. And that is sufficient to actually run a stochastic gradient algorithm now to minimize this compatible function approximation loss approximately. So I'm not actually going to plug in like an actor-critic style value function here necessarily, because that will indeed like, bring another mess of function approximation that I have to deal with that I really want to avoid. And it will also force me to make these stronger type of assumptions that Nan was making in the morning. So the algorithm we do analyze for finite sample setting is basically you obtain unbiased estimates of the gradient by just using Monte Carlo estimates of the advantage function. And that you can just, and then you can just like give, basically your epsilon approx now ends up being whatever it was plus something like a regret guarantee that you get for the online learning algorithm that you're using to minimize this function. And you can then easily quantify the role that the number of samples plays. And it's all like there aren't any bad surprises there. It ends up being quite clean. Peter?
So
That suggests that you might be able to relax the epsilon prox to be something that's more stringent in the neighborhood of the theta star and less stringent as you're further away. Is that the case?
Possibly.
At the moment, it seems like a very stringent thing that you have to have.
Yes. No. So yes, you're absolutely right in a way that I only care about kind of an average of those quantities, and so you could like put a schedule on how you want these things to behave. But the other way of viewing it is that these are not really quantities that the algorithm is using in any way, right? So it's an artifact of the analysis, and as long as you're right, you have any sequence of epsilon t's, which is maybe large somewhere, small somewhere, and so on, but along the sample path, it eventually adds up to or averages out to something small, things should be well behaved. But at least the nice thing is the algorithm wouldn't need to know how that's evolving. So it's not like I'm necessarily even imposing a schedule on those. If they end up behaving in a way that they average out properly, things will be fine. Yeah, okay. That's basically, I'm done. Good. So the goal in this paper was to try and give finite time convergence analysis for policy gradient methods given their wide use in practice. In doing so, we got a few different, few interesting observations. One is this distribution mismatch type quantity, which had been used in CPI before, really also seems to give a lot of leverage in these algorithms. Crucially, it does not necessarily require restricting the MDP dynamics, which is nice in contrast to some of the assumptions required in value function based learning. What I didn't talk about today is we do handle so everything here was sort of unprojected gradient based updates when your policy parameterization is such that you don't need to do projections. If it is such that you need to do projections, then things get a little bit more technical, and we do give results for that in the paper as well. And finally, this compatible function approximation loss seems to be a nice way to characterize the expressivity of the policy class. I think some of the future directions from here are pretty natural. So somebody already asked if the scale versus reverse scale business has been empirically investigated, and yeah, doing a proper empirical investigation there I think might be quite interesting. I mean, the other thing that really seems to be interestingly different here is I think Mohammad's question was foreshadowing this a little bit already, that actor-critic algorithms, so the way they've been usually analyzed is you first worry about the convergence of the value function, which forces you to make the same type of assumptions that you require for value function learning to succeed, and then you just view the remaining part as an approximate policy iteration operator. The natural actor-critic style analysis here is quite a bit different, and it'd be interesting to see if that makes a tangible impact in any empirical situations as well. This paper was getting pretty out of hand, so we chose to omit any discussion of variance reduction techniques here. But that's obviously very important when doing policy gradient methods practically, and it would be important to study those in conjunction with the framework we've developed here. And while I kind of keep on picking on these concentrability coefficients for putting assumptions on MDP dynamics, they're also more problem dependent because they can leverage MDP dynamics, which right now our quantities are not. So it would be kind of interesting to think about what are better problem dependent quantities that we can use to characterize convergence guarantees. And finally, one thing that maybe seems somewhat interesting to think about is that if we can characterize how the initial distribution mu affects the convergence properties of these algorithms, then could we also observe the dynamics of the algorithm itself and use it to improve the distribution mu itself as a device for basically designing exploration techniques for reinforcement learning? So I'm going to leave you with those thoughts. If you want to learn more, the paper did go up on arXiv just last Friday, and I'm happy to answer any questions.
this softmax setting help in the batch case when you have no simulator, you just have like data in the batch?
So that's going to take us into the territory of off-policy policy optimization. We have done some recent work on that, but we haven't quite merged the theory here, which we only just finished working on with the algorithms there. But if you are in the batch settings and you want to do policy optimization algorithms, Li Hong has some very nice work on policy evaluation settings, and we have some work in the policy optimization setting that might be of interest.
Just maybe a little bit different. Like you mentioned this distribution shift quantity, something like that. I was wondering, in the continuous space, like when S is continuous, is there any like analog of that?
I mean, you can still assume it even in a continuous state space. It's an L infinity norm.
X over S?
Yeah, that's what we formally assume in the paper. But like I was saying, the way it's coming up is you are trying to say that I have a small regression error under one distribution. I want to have a small regression error under a different distribution. And when can I do this transfer? And at the minimum, like you could, for instance, instead of L infinity L1, do a different holder. Like you do L2 L2, you end up with like an L2 norm of those, but you end up with a slightly worse dependency on the approximation error. So there is, and more generally, like, okay, Shai is not in the room. Otherwise, he would have told me that he's done years of work on trying to characterize when does learning transfer between two distributions using all these nice hypothesis class dependent notions, right? And there is no reason we couldn't leverage all of that very nice work here. So it's that's kind of the part I like about the function approximation case here, that we are probably giving the most pessimistic result that you could have extracted from that point, but there is room to actually do a lot better. Other Shai.
Very nice talk. So you basically show that with natural gradient, policy gradient becomes very similar to policy iteration.
Yes.
So how are the bounds? So what is the advantage then over policy iteration in terms of the theoretical bounds?
Good. Very nice question. So I guess few things. So in the exact gradient setting, you're indeed right that natural policy gradient and policy iteration become very similar, at least for the tabular setting. Now the problem is, and by the way, it's not, I mean, I would say like regularized policy iteration, like all of this entropy regularized policy iteration really. Right, the problem is I don't think the equivalence is quite as tight once we go to function approximation, because now the way natural, the usual approximate policy iteration would happen is you would say, well, okay, I still want to just do policy iteration for the policy itself, so go do whatever you are going to do for value function approximation, because that's the, and then I will be sort of completely non-parametric in my choice of policy with respect to that value function, right? I'm just still going to do something like a max or a softmax. And here, I feel like maybe it's the part that is qualitatively different is that you're actually finding the best policy from a parameterization over policies, which sort of the policy iteration doesn't necessarily give you a very nice way to think about, right? So when you have a restricted policy class, I do find this viewpoint a little bit nicer. At the same time, actually, a lot of the theory that's going on here is in some ways not that, I mean, you can construct a lot of parallels between the type of analysis here, well, not analysis, the type of results we get here and the type of results, for instance, conservative policy iteration gets, except CPI doesn't give you a compact way of representing the final policy. Like you have to keep all these policies you found along the sample path around. And that's, I think, like one of the reasons people don't necessarily use that algorithm in practice, even though it's a good algorithm. And here, like, because you keep on updating your parameter, you always have a compact representation of your policy. So just empirically, this, I think, does seem to certainly offer some conveniences. And the other reason is we are interested in these type of algorithms is that people certainly seem to be using a lot of these, like natural gradient type algorithms, at least from a 10,000 feet level, also look very similar to all these TRPO type algorithms, which people certainly seem to use in practice. So it's interesting to think about what we can say from those methods. But yes, there are certainly a lot of similarities with regularized policy iteration.
I think we'll take further questions offline. So let's thank the speaker again.
Back at 2:15.